Hello there, and welcome to Deep Sleep Seas. I'm so glad you found your way here tonight. Maybe you've had a long day, or perhaps you're someone who finds comfort in drifting off to the gentle rhythm of ocean mysteries and hidden wonders beneath the waves. Either way, this journey is for you. You have nothing to do right now but rest. Let your breathing slow, your muscles soften, and your mind begin to wander as we descend together into some of the most peaceful ancient places on Earth. Tonight we're exploring underwater caves. Not the dark, frightening spaces you might imagine, but serene sanctuaries carved over millions of years, filled with crystal clear water that filters sunlight into dancing beams of blue and gold. These are places where time moves differently, where a single water drop takes centuries to build a stone icicle, where fish have learned to navigate eternal darkness with grace, and where the very walls hold secrets from ages long before humans walked the earth. We'll drift through flooded limestone chambers in Mexico, where the ancient Maya believed doorways to the underworld opened into pools of turquoise water. We'll descend into blue holes that plunge hundreds of feet into the ocean floor, their circular openings like eyes gazing up at the surface world. We'll meet creatures that have evolved to thrive without ever seeing sunlight, and we'll trace the patient work of water as it sculpts stone into formations of breathtaking delicacy. Some of what you hear tonight may surprise you. Most of it will simply wash over you like a gentle current, carrying you deeper into rest. These caves have been forming for longer than you can imagine, and they will continue their slow transformation long after we're gone. There is something deeply calming in that continuity, that patient reshaping of the world by the simplest of elements: water and stone, darkness and time. Before we begin our descent, if these calm explorations help you unwind or offer you a peaceful way to close your day, consider liking and subscribing to the channel. It helps others discover these gentle journeys too, one restful soul at a time. Now let's take a breath together and begin our journey into the quiet depths. The entrance to the cave is just ahead, a pool of water so clear it's almost invisible, reflecting the sky above while concealing the mysteries below. Underwater caves begin their existence, not in water at all, but in air, formed during ancient times when the world was a very different place. To understand these spaces, we must think in geological time, where a million years passes like a single season, where continents drift and oceans rise and fall with the patient rhythm of planetary breathing. Most underwater caves that we know today were carved from limestone, a rock that seems solid and eternal to us, but is actually quite vulnerable to the gentle persistence of water. Limestone itself is made from the shells and skeletons of ancient sea creatures, compressed over eons into thick layers of carbonate rock. It is, in essence, a graveyard made solid, turned to stone, and then hollowed out again by time and chemistry. The formation begins with rain. As rainwater falls through the atmosphere, it absorbs carbon dioxide, becoming slightly acidic. This weak acid grows stronger as it filters through soil and decaying plant matter, picking up more carbon dioxide along the way. When this acidic water encounters limestone, a slow chemical reaction begins. The acid dissolves the calcium carbonate in the rock, carving out tiny channels and fissures. Over thousands of years, these channels grow larger. Water follows the path of least resistance, always seeking the lowest point, always finding the cracks and weaknesses in the stone. At first, these passages might be no wider than a hair, but water is patient. Drop by drop, year after year, the channels widen. Small streams become underground rivers, narrow fissures become chambers large enough to swallow buildings. The process happens so slowly that if you could watch a single section of limestone for your entire lifetime, you would see no change at all. Yet over 10,000 years, over 100,000, over a million, the transformation is complete. During the Ice Ages, which occurred multiple times over the past 2.5 million years, vast amounts of water became locked in glaciers and ice sheets. Sea levels dropped by as much as 400 feet below where they are today. Coastlines extended far beyond their current positions. Land that is now underwater was dry, and in that exposed limestone, caves could form in the air, shaped by dripping water and underground streams that had never seen the ocean. These Ice Age caves grew spectacular formations. Stalactites hung from ceilings like stone icicles, growing downward at a rate of perhaps an inch every 100 years. Stalagmites rose from floors where water droplets splashed and deposited their tiny cargo of dissolved minerals. Columns formed where stalactites and stalagmites met after thousands of years of growing toward each other. Flowstone covered walls in rippling curtains of calcite. Every drop of water that fell in darkness left its mark, building these stone gardens in absolute stillness and blackness. Then the ice ages ended, as they always do. The great ice sheets melted. Water that had been frozen for thousands of years returned to the oceans. Sea levels rose slowly, inexorably, flooding coastal areas and low-lying lands, and the caves, those chambers carved during the Ice Age, began to fill with water. What had been dry passages accessible only to land creatures became submerged corridors, navigable only by those who could breathe underwater or hold their breath for impossibly long times. But the caves preserved their Ice Age architecture. The stalactites and stalagmites, which can only form in air where water can evaporate and release its dissolved minerals, stopped growing. They became frozen in time, hanging in clear water, monuments to an era when the cave was dry and the ocean was elsewhere. Today, when divers explore these flooded chambers, they swim past formations that took tens of thousands of years to grow, formations that will never add another molecule of stone because they are now submerged. Not all underwater caves formed this way. Some, called sea caves, are carved directly by wave action. The ocean pounds against coastal cliffs, exploiting weaknesses in the rock, hollowing out chambers at the waterline. These caves are different from the flooded Ice Age caves. They tend to be shorter, less complex, their walls marked by the violence of waves rather than the patient dissolution of acidic groundwater. But they too have their beauty, their own forms of peace, especially in calm weather when the water within them grows still and reflects the rocky ceiling like a mirror. Blue holes represent yet another variation on the theme. These are essentially vertical caves, often circular in shape, that drop straight down into the seafloor. From above, they appear as dark blue circles in the lighter turquoise of shallow water, hence their name. Many blue holes were formed as sinkholes during the Ice Age, when the limestone surface collapsed into underground cavities. When the sea rose, these sinkholes filled with water, becoming deep wells in the ocean floor. Some connect to extensive horizontal cave systems. Others are isolated vertical shafts, dropping into darkness. The cenotes of Mexico's Yucatan Peninsula tell a particularly fascinating story. The word cenote comes from the Mayan term dozanot, meaning sacred well. The Yucatan is essentially a massive limestone platform with almost no surface rivers. All the water flows underground through an intricate network of caves and channels. Cenotes are natural openings where the limestone ceiling has collapsed, creating access to the underground river system. There are thousands of them scattered across the peninsula, and many are connected below the surface through flooded caves that stretch for hundreds of miles. These cenotes were crucial to Mayan civilization. In a landscape without surface water, the cenotes provided access to the life-giving underground rivers. The Maya considered them sacred, portals to Egbolba, the underworld of their mythology. They made offerings in the cenotes, sometimes of precious objects, sometimes of human sacrifice. When archaeologists and cave divers explore these cenotes today, they sometimes find ancient pottery, jade, gold, and human bones resting in the sediment, offerings made 1,000 years ago to the gods of the underworld. The formation of each cenote is unique. Some began as large chambers whose ceilings grew thin and eventually collapsed all at once, creating open pools at the surface. Others formed more gradually, with small holes that widened over time. Some cenotes are fully open to the sky, while others retain most of their ceiling, with only a small hole letting in a shaft of light. The variety is endless, each cenote a unique sculpture created by geology, time, and chance. What makes these underwater caves so mesmerizing is not just their formation, but what they preserve. They are time capsules. The water that fills them has often been filtered through limestone for hundreds or even thousands of years. It is among the purest, clearest water on Earth. The formations they contain grew over timescales that dwarf human history, and the life that has adapted to them represents millions of years of evolution in isolation. As you rest tonight, imagine water seeping into stone year after year, century after century. Imagine chambers growing in darkness beneath ancient forests, beneath oceans, beneath ice. Imagine the patient work of chemistry and gravity, never hurrying, never pausing, simply continuing their slow transformation of solid rock into hollow space, into a realm where water and stone dance together in a partnership that spans millions of years. Around our planet, scattered across tropical coasts and hidden in deep ocean floors, lie some of the most extraordinary natural formations ever discovered. These are the great underwater cave systems, each one unique, each one holding mysteries that scientists are still working to understand. Let's visit some of these remarkable places, drifting through their stories like a gentle current. The Sistema Saskatoon, located beneath the jungle floor of Mexico's Quintana Roo state near Tulum, held the title of the world's longest underwater cave system for many years. Its name means White Cave System in Mayan, and it stretches for more than 216 miles of surveyed passages. This is not a single cave, but a vast network of interconnected tunnels, chambers and cenotes, all filled with crystal clear water. Exploring it in its entirety would take many human lifetimes, and even now, new passages are being discovered and mapped. Divers who enter Sistema Saskatoon describe it as otherworldly. The water is so clear that visibility can exceed 300 feet. You can see from one end of a vast chamber to the other, every stalactite perfectly visible, every formation crisply defined. The passages wind through every conceivable configuration. Some are grand galleries tall enough to contain a house, others narrow to gaps that a diver must squeeze through sideways. There are rooms filled with ancient formations, passages that slope down into deeper darkness, and shafts that rise towards cenotes where daylight filters through in celestial beams. What makes Sistema Saskatoon particularly special is its archaeological significance. Throughout the system, divers have discovered human remains and artifacts from the Ice Age, when these caves were dry. The bones found here are among the oldest human remains in the Americas, dating back more than 10,000 years. They tell the story of people who explored these caves when they were air-filled, perhaps seeking shelter, perhaps conducting ceremonies, perhaps simply curious about the darkness. Now their bones rest in eternal peace beneath hundreds of feet of limestone, cradled by the same passages they once walked. Not far from Saskatoon lies Sistema Ox-Bell-Ha, whose name translates to 3 paths of water. For a time before the two systems were proven to be connected, Ox-Bell-Ha vied with Saskatoon for the title of world's longest underwater cave. Even as a separate system, it measured more than 167 miles of passage. The caves are remarkably complex, with multiple levels of passages stacked on top of each other, carved at different times when sea levels were at different heights. Swimming through Ox-Bell-Ha is like moving through the pages of a geology textbook, each level telling a different chapter in the Earth's climatic history. The cenotes that provide access to these systems are themselves worth contemplating as you drift towards sleep. Grand Cenote, near Tulum, is perhaps the most visited. It's a partially collapsed cave with sections open to sunlight and sections that descend into darkness. When sunlight enters the water here, it creates rays of light that slice through the clarity like visible pathways, illuminating the stalactites and highlighting each ripple on the surface. Divers and snorkelers share the space with small fish and occasionally with freshwater turtles that have made the cenote their home. Cenote Angelita, or Little Angel, offers one of the most surreal underwater scenes on Earth. At about 90 feet deep, beneath a layer of fresh water, lies a river. Not an underground river, but a river within the water, formed by a layer of hydrogen sulfide that creates a distinct boundary between the fresh water above and the salt water below. This boundary looks exactly like a riverbed, with trees rising from it. These aren't real trees, but rather dead tree trunks that have been preserved by the sulfur-rich water. Divers can hover above this false river, looking down at the ghostly forest, experiencing one of nature's most unusual optical illusions. Across the Caribbean in Belize lies the Great Blue Hole, perhaps the most photographed underwater cave entrance in the world. From the air, it appears as a perfect circle of deep blue set in the lighter turquoise of the surrounding shallow reef. This circle is over 1,000 feet across and descends to a depth of about 400 feet. The Great Blue Hole was made famous by Jacques Cousteau, who declared it one of the top diving sites in the world. He brought his ship Calypso here to explore and chart its depths, introducing it to the wider world. The Blue Hole began as a cave system during the Ice Age. As ice melted and sea levels rose, the cave system flooded. Eventually, the ceiling of this massive chamber collapsed, creating the circular sinkhole we see today. Inside, the walls are lined with stalactites, some of them massive, hanging in the dark water like stone fangs. These formations grew when the cave was dry, and their presence proves that the blue hole was once a vast air-filled chamber. The stalactites angle in specific directions, and by studying their orientation, geologists can determine that the cave experienced multiple flooding events as sea levels rose in stages during different melting periods. Deep in the blue hole, at around 300 feet, there is a layer of water that contains hydrogen sulfide. This layer is anoxic, meaning it contains no oxygen. Nothing can live below this boundary. When submarine expeditions explored the very bottom of the blue hole, they found the bodies of divers who had perished during previous explorations, preserved in the oxygen-free environment. Out of respect, these remains were left undisturbed, resting in the silent depths. In the Bahamas, Dean's Blue Hole holds the record as the world's deepest known blue hole, measured from the entrance to the verified bottom at 663 feet. It's located in a bay on Long Island, and from the surface, it appears as a dark circle in shallow turquoise water, its walls dropping vertically into darkness. The entrance begins at about 65 feet deep, then opens into a massive chamber that plunges straight down. Free divers are drawn to Dean's Blue Hole because the descent path is clear and unobstructed, allowing them to test their depth limits in relatively safe conditions compared to open ocean diving. But the record for deepest blue hole may not belong to Dean's. In 2024, scientists announced that the Tame-Jub Blue Hole in Chetumal Bay, Mexico, extends to at least 1,380 feet below sea level and possibly deeper. The research team hasn't reached the bottom yet. Their instruments could only go down to about 1,640 feet, and they met an obstruction at 1,380 feet. It might be the bottom, or it might be a ledge with deeper chambers below. Water analysis at the deepest measured point suggests the hole may connect to the Caribbean Sea through hidden underwater tunnels, as the water chemistry matches that of the open ocean. These measurements are humbling. Dean's Blue Hole could swallow a 60-story building and still have room at the top. Tame-Jub could hide a structure twice that height. And these are just the spaces we can see, the vertical shafts. They may connect to horizontal passages that extend for miles, entire underground seascapes that have never been seen or mapped. In the Bahamas, there are more than 200 blue holes in total, scattered across the islands and surrounding shallow banks. Andros Island alone has more than 175 inland blue holes and dozens more offshore. Many have never been explored beyond their entrances. Each one is potentially unique, possibly containing species found nowhere else, preserving geological records that could teach us about past climates or connecting to cave systems we don't yet know exist. Some blue holes experience tidal flows, so strong they become dangerous whirlpools. The Chimney Blue Hole off Grand Bahama acts like a giant bathtub drain when the tide comes in, sucking down millions of gallons of water in a vortex that can pull swimmers and even small boats into its depths. When the tide goes out, the flow reverses, and water comes boiling back up from the hole like an underwater geyser. These tidal blue holes are connected to cave systems that extend far beneath the island. As the ocean rises and falls, water is forced through these underground passages, creating the dangerous surface flows. The inland blue holes of the Bahamas are even stranger. Hidden in forests, appearing as dark ponds surrounded by jungle, these holes are stratified with distinct layers. On top sits a thin layer of fresh rainwater. Below that lies a thick layer of brackish water containing hydrogen sulfide, a toxic gas produced by bacteria consuming organic matter. This layer is often rust-colored or even purple, stained by the bacterial colonies. Below the hydrogen sulfide layer sits dense saltwater from the ancient ocean. These inland blue holes are time capsules preserving species that have lived in darkness for thousands of years, adapted to survive in water that would kill most creatures in minutes. Far from the tropical Caribbean, in the Mediterranean, there are underwater caves of a different character. The limestone coasts of France, Italy, Greece, and Croatia are riddled with sea caves carved by wave action over millennia. Some, like the Blue Grotto of Capri in Italy, are famous for the quality of light they produce. Sunlight enters the grotto through an underwater opening and reflects off the white sand bottom, creating an ethereal blue glow that fills the cave. The Romans knew of this grotto and built a passage to it, though that passage has since collapsed. Visitors today must enter by small boat at low tide, ducking as the boat glides through the narrow entrance into the luminous interior. Each of these systems, from the longest flooded caves of Mexico to the deepest blue holes of the Caribbean, from the mysterious inland holes of the Bahamas to the light-filled grottos of the Mediterranean, has its own character, its own story written in stone and water. They are places of extraordinary peace, where the only sounds are the gentle movement of water and perhaps the distant echo of your own breathing. Imagine floating in such a space now, suspended in crystal clarity, surrounded by formations that grew in darkness over thousands of years, part of a world that exists beneath the world, hidden, timeless, serene. One of the most striking features of underwater caves is the extraordinary clarity of their water. If you've ever swum in the ocean or a lake, you know that water is usually at least slightly cloudy, tinted by sediment, algae, or tannins from organic matter. Visibility might be 30 feet on a good day in the ocean, perhaps 50 feet in a very clear lake. But in underwater caves, visibility can exceed 300 feet. The water is so transparent that it barely seems to exist. Divers describe the sensation as flying rather than swimming, suspended in empty space with only the stone walls to provide reference. This remarkable clarity has a simple explanation that nevertheless takes centuries to achieve. The water in most underwater caves has been filtered through limestone for hundreds or even thousands of years. When rain falls on the surface, it begins a long journey. It seeps into the soil, percolates through layers of sediment, and eventually enters the porous limestone. The limestone acts as a natural filter, removing particles, sediments, and organic matter. The water moves slowly through this filter, perhaps traveling just a few feet per year, taking decades or centuries to complete the journey from the surface to the cave below. By the time the water reaches the cave, it has been purified to a degree that few water treatment plants could match. It contains almost no suspended particles. There are no algae, because algae need light to grow, and no light penetrates deep into the caves. There's very little organic matter, because most of that has been filtered out or consumed by microorganisms in the soil and upper layers of rock. What remains is water of almost distilled purity. In cenotes, the clarity is even more remarkable because the water has an additional quality. It is virtually mineral-free, having deposited most of its dissolved minerals in the slow process of dissolving and then redepositing limestone. This water is so pure that it has very little taste. It's cool, typically around 75 degrees Fahrenheit year-round in tropical cenotes, maintained at that temperature by the insulating effect of hundreds of feet of overlying rock. The clarity creates unique visual effects. One of the most mesmerizing is the halocline, a boundary between fresh water and salt water that exists in many cenotes and coastal cave systems. Fresh rainwater, being less dense, floats on top of heavier salt water that intrudes from the ocean through cracks and passages in the limestone. These two types of water don't mix well. They form a distinct boundary, and when you cross that boundary, the world seems to shimmer and blur for a moment before clearing again as you pass fully from one layer to the other. The halocline looks like an underwater mirage. It appears as a wavy, shifting surface within the water, often with a slightly different color or opacity. It's caused by the difference in light refraction between the fresh and salt water. Swimming through a halocline is a surreal experience, like passing through an invisible membrane between two different worlds. Above the halocline, the water is fresh and clear. Below it, the water is equally clear but saltier, and often slightly cooler. The boundary can be just inches thick, or it can extend over several feet, depending on how much mixing has occurred from currents and tides. Some haloclines are permanent features, stable for years in caves with little tidal influence. Others shift position with the tides or seasonal rainfall. In Cenote Angelita, the halocline is so distinct and stable that it creates the appearance of an underwater river, complete with a riverbed of hydrogen sulfide and trees preserved in the sulfur-rich water. Divers can hover at the boundary, looking down into what appears to be a completely separate aquatic environment below them. The temperature of cave water also contributes to its clarity. In tropical regions, the water temperature in deep caves is remarkably stable year-round, usually matching the average annual air temperature of the region. This stability means there are no temperature-driven currents to stir up sediment. The water is still, sometimes so still that it feels thick, resistant, as if you're moving through something denser than normal water. Some divers describe it as feeling like flying through air that has substance. In blue holes, the clarity extends to astonishing depths. In Dean's Blue Hole, visibility of over 100 feet is common throughout the first few hundred feet of descent. The walls drop vertically, clean limestone face with occasional ledges and overhangs. Looking up from 200 feet down, you can see the circle of light at the entrance, a bright disk floating impossibly far above you. Looking down, the darkness increases gradually, the blue fading to purple, then to black as you descend beyond the reach of sunlight. The absence of sediment in these caves means that formations are often pristine, unmarred by the accumulation of silt or mud that obscures so much underwater in rivers and oceans. Stalactites in flooded caves appear as they did when they stopped growing thousands of years ago. Their surfaces are clean, their crystal structure visible, their calcite layers distinct. If you were to carefully examine a stalactite in a flooded cave, you could see the concentric rings of growth, like tree rings, each ring representing a period of time when water dripped and minerals precipitated. The water's clarity also means that colors are preserved to greater depths than in the open ocean. In most underwater environments, red wavelengths of light are absorbed within the first 20 feet, making everything appear blue-green below that depth. But the extraordinary transparency of cave water allows red light to penetrate deeper. If you were to shine a light on red formations at 100 feet deep in a cave, they would appear red, not the washed-out brown or gray they would appear at that depth in the ocean. This visual clarity creates an environment of unusual peace. There is no haze, no murkiness, no mystery about what lies in the distance. Everything is visible with perfect definition. It's the opposite of the ocean, where visibility is limited, and every dive feels like moving through fog. In a cave, the limitations come not from the water, but from the light. Where light reaches, you can see everything. Where light does not reach, there is only profound darkness. Some divers describe the experience of being in such clear water as disorienting. Without particles in the water to provide visual reference, without the subtle haziness that helps us judge distance, it becomes difficult to tell how far away something is. A stalactite might be 10 feet away, or 50. A wall might be close enough to touch or well out of reach. Your brain lacks the familiar cues it uses to judge distance underwater, and the result can be a dreamy, floating sensation where scale and space seem uncertain. Imagine now, as you settle deeper into rest, floating in water so clear it's invisible. You're suspended in perfect stillness, surrounded by stone that was carved before humans existed, held by water that has been purified over centuries, part of a place where time moves according to geological rhythms, rather than the frantic pace of the surface world. The temperature is perfect, cool but not cold. The clarity is absolute, and you are floating, weightless, peaceful, in a space between the solid earth and the liquid realm, between darkness and light, between the ancient past and the patient present. In the underwater caves we've been exploring, particularly in those that were once dry during the Ice Age, there hang and rise formations of surpassing delicacy and beauty. These are the stalactites and stalagmites, the stone icicles and stone towers that grow with such patience that they make glaciers seem hurried by comparison. To understand these formations is to comprehend a timescale so vast it defies easy imagination, yet so simple in its mechanism that a child could grasp the principle. Stalactites hang from cave ceilings. The word comes from the Greek stalaktos, meaning dripping, and that is exactly how they form. A drop of water, saturated with dissolved calcium carbonate from its journey through limestone, hangs from the ceiling. The cave air has lower carbon dioxide content than the water, so as the drop hangs there, carbon dioxide begins to escape from the water. This loss of CO2 changes the water's chemistry, causing a tiny amount of calcium carbonate to precipitate out of solution, forming a thin ring of calcite exactly where the drop clings to the ceiling. The drop falls. Another drop forms in the same place, hangs, loses CO2, deposits its own ring of calcite and falls. Drop by drop, ring by ring, a tube begins to form, hollow, fragile, called a soda straw, stalactite, for its resemblance to a thin drinking straw. These soda straws can grow quite long, sometimes reaching several feet in length, but they remain incredibly delicate, with walls only about the thickness of paper. If the soda straw becomes plugged with a calcite crystal or a bit of sediment, Water begins to flow down the outside instead of through the center. Now each drop leaves its calcite on the exterior, and the stalactite begins to widen, developing the classic cone shape we associate with these formations. The wider it grows, the slower its growth rate becomes, because the same amount of water must now deposit minerals over a larger surface area. A mature stalactite might be several feet in diameter and dozens of feet long, having grown over tens of thousands of years. The rate of stalactite growth varies depending on many factors: the amount of water, the concentration of dissolved minerals, the temperature and humidity of the cave, even the smoothness of the surface where drops hang. But in general, stalactites grow very slowly. In temperate regions, a rate of about 1 inch per century is typical, though in tropical areas with higher rainfall and more dissolved minerals, growth might be somewhat faster. This means that a stalactite 1 foot long took at least 1,000 years to form, probably much longer. A formation 10 feet long might be 20,000 years old or more. Stalagmites rise from cave floors where water drips from above. The word comes from stalagma, Greek for dropped, referring to the drops that build them. When a drop falls from a stalactite and strikes the floor, it splashes, loses more CO2, and deposits more calcium carbonate. The impact spreads the water slightly, so stalagmites tend to be wider and more blunt than their stalactite counterparts. They grow upward toward the source of the drips, gradually building rounded columns or towers that can eventually reach the ceiling. Stalagmites actually grow slightly faster than stalactites, because the splashing action of the dropping water accelerates the loss of CO2 and the deposition of minerals. But we're still talking about timescales measured in centuries and millennia. A stalagmite might grow an inch in 50 years under ideal conditions, perhaps an inch per 100 years in drier caves. The growth rings inside a stalagmite can be counted like tree rings, and each ring can be dated using various radiometric techniques, providing a record of cave conditions at different times in the past. Sometimes, after thousands of years, a stalactite and stalagmite growing toward each other finally meet. Their tips touch, and they begin to fuse, forming a column. This column will continue to thicken as long as water continues to drip, though the growth becomes even slower as the formation grows wider. Some columns in ancient caves are tens of feet thick, representing hundreds of thousands of years of continuous growth. But in the underwater caves we're exploring tonight, these formations are frozen in time. They stopped growing the moment the cave flooded, because stalactites and stalagmites can only form in air. They need the water to evaporate or release CO2 to the cave atmosphere. Underwater, there's no air for the CO2 to escape into, no evaporation, no deposition. So the formations that grew during the Ice Age, when these caves were dry, have been perfectly preserved for the 10 or 15,000 years since the sea rose and flooded them. Swimming past these formations in a flooded cave is like visiting a museum of the Ice Age. Every stalactite is exactly as it was the day the water arrived. If a stalactite was growing from a soda straw and had just begun to widen, it remains at that exact stage of development. If a stalagmite was within inches of touching its corresponding stalactite, they remain that same distance apart, their kiss interrupted by the rising sea, frozen in their moment of near union for thousands of years. Other formations also grace these caves. Flowstone forms where water flows in sheets over walls or floors, depositing layers of calcite in rippling, frozen waterfalls of stone. Draperies form where water flows along ceiling cracks, building delicate curtains of calcite, sometimes translucent, sometimes colored by minerals other than calcite. Helictites grow in seemingly impossible directions, defying gravity, their growth driven by capillary action and crystallization pressure rather than the simple force of falling water. They curl and twist, resembling roots or coral, or sometimes nothing found in nature, purely abstract mineral sculptures. Some of the longest stalactites in the world hang in underwater caves. In Gruta, Rei do Mato in Brazil, a limestone stalactite measures 66 feet long, though it's not underwater. But in flooded caves in Mexico, stalactites nearly as long hang in crystal clear water, illuminated by divers' lights, casting shadows on the walls, silent witnesses to ages we can barely conceive. The Sun Dune Cave in Vietnam, primarily a dry cave but with flooded sections, contains stalagmites over 200 feet tall, some of the tallest known to science. These were built by water dripping for millions of years in a chamber so vast that entire city blocks could fit within it. Though not underwater, they remind us of the scale at which these processes can work, given enough time. In the underwater caves we're exploring, the formations are typically smaller, but no less impressive for their perfect preservation. A 3-foot stalactite that stopped growing 15,000 years ago is still in pristine condition, its surface unmarred by the passage of time underwater. If you could somehow remove the water, it could begin growing again immediately, picking up exactly where it left off. The colors of these formations vary depending on the minerals present. Pure calcite is white or clear, but tiny amounts of iron oxide can create shades of orange, brown, or rust. Manganese can produce blacks and grays. Copper creates blues and greens. The combinations create subtle beauty. A white column with brown bands, a golden curtain of drapery stone, a cluster of rust-red helictites against gray limestone. These colors are muted underwater, but with the right lighting, they glow with soft, earthy tones. The silence in which these formations exist is profound. In a dry cave you might hear water dripping, the source of the formations themselves. In a flooded cave, even that sound is absent. There is only stillness, only the occasional sound of your own breath, only the patient presence of stone structures that grew in darkness before and will rest in darkness forever, monuments to the simple, inexorable chemistry of calcium carbonate and time. As you drift towards sleep, imagine a single drop of water clinging to stone, releasing its burden of dissolved minerals, falling to splash on the floor below. Imagine this repeated 10 million times, 100 million times, each drop leaving its microscopic contribution. Imagine formations growing in absolute darkness, never seen, never touched, simply continuing their patient construction in the silence beneath the earth. Imagine them now, underwater, bathed in the beam of a distant diver's light, casting shadows, perfectly still, waiting in the timeless calm of flooded stone chambers. Blue holes hold a special place in human imagination. Their circular forms, their gradient of blues from pale turquoise at the rim to deep indigo at the center, their mysterious depths all combine to create a sense of wonder mixed with a touch of trepidation. These formations are windows into the underworld, vertical caves that plunge straight down, often to depths that exceed the reach of conventional scuba diving. The name blue hole describes exactly what you see from above. In shallow water, typically on a carbonate platform like the Bahamas, the ocean appears bright turquoise or aquamarine due to sunlight reflecting off the white sand bottom. But where a blue hole opens, the color changes dramatically. The hole appears dark blue, almost purple, because the light is not reflecting back from shallow sand but rather disappearing into deep water. The greater the depth, the more light is absorbed, the darker the blue becomes. The contrast between the pale surrounding water and the deep blue of the hole is striking, creating a perfect circle or oval that seems to gaze up at the sky like a massive eye. Most blue holes are ancient sinkholes that formed during the ice ages when sea levels were lower and the limestone platforms were exposed land. Rainwater seeped through cracks, dissolved the limestone, created caves and caverns. Eventually, the ceilings of these caverns collapsed, leaving vertical pits opening to the sky. When the ice melted and seas rose, these pits filled with water, becoming the blue holes we see today. The walls of blue holes are typically vertical or near-vertical limestone, sometimes undercut where softer layers of rock have eroded more quickly than harder layers. Looking down from the rim of a blue hole, you can sometimes see ledges at various depths, marking old sea levels. Each ledge represents a time when the sea was at that level for long enough to erode a horizontal notch in the limestone. By studying these ledges, geologists can reconstruct the history of sea level changes over the past 100,000 years or more. Descending into a blue hole is an experience unlike any other form of diving. You drop vertically through water of remarkable clarity. The walls pass by on all sides, close enough to touch. Light fades gradually as you descend, the bright turquoise of the surface changing to deeper blues, then to purples and finally to darkness. If you look up, the entrance remains visible as a circle of light, growing smaller and more distant as you go deeper. At certain depths, often around 200 to 300 feet, some blue holes contain a halocline, a boundary between less dense fresh or brackish water above and dense salt water below. This halocline can also contain hydrogen sulfide, a byproduct of bacterial decomposition of organic matter. The hydrogen sulfide layer is sometimes visible as a hazy cloud or as a distinct color change, from clear blue water above to murky brown or purple water below. This is the boundary between the oxygenated zone where life can exist and the anoxic zone below where nothing that needs oxygen can survive. Below the hydrogen sulfide layer, conditions are harsh. The water is acidic from the dissolved sulfur. There's no oxygen, no fish, no plants, not even the usual bacteria that decompose organic matter in oxygenated environments. What little life exists here consists of specialized bacteria that can process sulfur compounds, deriving energy from chemical reactions rather than from oxygen. These bacteria form mats and colonies, sometimes creating elaborate structures on the walls and floor of the deep zone. The connection between blue holes and horizontal cave systems is one of the most intriguing aspects of these formations. Many blue holes are not simple vertical shafts but are connected to extensive networks of submerged passages extending horizontally through the limestone. These passages may connect multiple blue holes or may extend for miles beneath the seafloor before emerging at another location. Exploring these horizontal passages requires advanced cave diving skills and equipment. The passages can be narrow, forcing divers to remove equipment and push it ahead of them to fit through restrictions. They can be complex, branching and rejoining in confusing patterns. Silt on the floor can be stirred up by the slightest disturbance, reducing visibility to 0 in seconds. Divers use continuous guidelines, essentially long ropes that they follow into the cave and back out, because getting lost in such an environment is often fatal. The line becomes literally a lifeline, the only thing connecting them to the exit and to life. Yet despite these dangers, blue holes have been extensively explored. Divers have mapped hundreds of miles of passages beneath the Bahamas, Mexico, and other limestone platforms. They've discovered entire systems of caves that no one knew existed, some of them rivals in length to the great terrestrial cave systems of the world. And they continue to explore, pushing deeper, extending the known maps, occasionally finding new blue holes that provide access to previously unreachable sections of the underwater maze. The tidal flows in blue holes can be dramatic. Holes that connect to extensive cave systems experience significant water movement as the tide rises and falls. The ocean pushes water into the holes at high tide and pulls it back out at low tide, forcing water through the connecting passages. In some cases, the volume of water moving through these passages creates strong currents, even dangerous vortices at the surface where water is being pulled into the hole. Chimney Blue Hole in the Bahamas is notorious for its tidal whirlpool. At certain stages of the tide, water pours into this hole with such force that it creates a vortex 10 or 15 feet across, powerful enough to pull swimmers underwater. The locals know to avoid it during these times, and there are signs warning visitors of the danger. Yet during slack tide, when the tidal flow pauses before reversing, the hole becomes placid, allowing safe exploration. The timing of dives in tidal blue holes requires careful planning based on tide charts and local knowledge. Inside the deeper zones of blue holes, conditions are remarkably stable. Temperature remains constant year-round, typically matching the average annual temperature of the deeper ocean at that latitude. Salinity is stable, current is absent except during tidal exchanges. This stability has allowed some blue holes to preserve remarkable records of past climates. Sediment cores taken from blue hole floors contain layers of mud and organic material that have accumulated over thousands of years. By analyzing these layers, scientists can determine what the climate was like at different times in the past, what plants were growing in the region, even what animals were present. Some blue holes have preserved the bones of animals that fell into them during the Ice Age. In Sawmill Sink in the Bahamas, paleontologists have recovered bones of giant sloths, tortoises, crocodiles, and other species that lived in the Bahamas when it was much larger and the climate was cooler. These animals fell into the sinkhole, which was probably filled with water even then, and their bones accumulated on the bottom, becoming fossilized over thousands of years. Now those fossils lie in deep water, a window into an ecosystem that no longer exists. Human remains have also been found in some blue holes. In Hoyo Negro, a blue hole in Mexico, divers discovered the nearly complete skeleton of a young woman who lived about 13,000 years ago. She apparently fell into the pit, which was dry at the time, and died from her injuries. Her bones lay undisturbed until divers found them, representing one of the oldest and most complete human skeletons ever found in the Americas. They named her Naya, and her bones have provided valuable genetic information about the peopling of the American continents. The mystery and beauty of blue holes continue to draw explorers, scientists, and filmmakers. They are photogenic in a way few underwater formations are. Their perfect circles and gradient colors, creating compositions that seem almost too perfect to be natural. Documentary crews have filmed extensively in blue holes, capturing footage of divers descending into the darkness, swimming through crystal-clear water, exploring passages decorated with ancient stalactites and stalagmites. As you rest tonight, imagine hovering at the edge of a blue hole, looking down into that circle of deepening blue. Imagine descending slowly, the walls rising around you, the circle of light above growing smaller. Imagine the transition from the bright surface world to the calm, dark interior, from the rush of waves and wind to the utter stillness of deep water. Imagine floating in that blue vastness, suspended between the illuminated shallows and the mysterious depths, held in perfect equilibrium, peaceful, safe, gradually letting yourself sink into deeper rest. Deep in the underwater caves and blue holes we've been exploring, far from any hint of sunlight, there exists life. It seems impossible at first consideration. How can anything live in complete darkness, in water that is often oxygen poor, in an environment that receives no input of energy from the sun? Yet life persists, adapted in ways both elegant and strange, creating ecosystems unlike anything found in the sunlit world above. The creatures that live exclusively in caves are called troglobites, from the Greek words for cave and life. In aquatic caves, they're sometimes specifically called stygobites, named after the river Styx of Greek mythology, the river that separated the living world from the underworld. These are not occasional visitors to caves, not creatures that hide in caves during the day and emerge at night. They are permanent residents, species that have lived in caves for so many generations that they have lost the ability to survive anywhere else. The most striking feature of many troglobites is their lack of eyes. In absolute darkness, vision provides no advantage. Eyes are complex organs that require significant energy to build and maintain. Natural selection gradually eliminates unnecessary energy expenditures, so in the eternal night of deep caves, eyes become vestigial, then disappear entirely. Cave fish are often born with tiny eye buds that never develop, becoming covered by skin as the fish matures. The result is a fish that appears smooth where its eyes should be, blind but not disadvantaged, because in its world there is nothing to see. But troglobites are not helpless in darkness. They have enhanced other senses to compensate for the loss of vision. Many cave fish have exceptionally sensitive lateral line systems, arrays of pressure-sensing organs along their sides that detect the slightest movements and pressure changes in the water. They can sense a nearby wall, an approaching predator, or potential prey without seeing any of them, navigating by feel in a way sighted fish cannot match. Cave fish also often have enhanced chemical sensing abilities. Their sense of smell is acute, allowing them to detect food or mates by following chemical trails in the water. Some species have taste buds all over their bodies, not just in their mouths, essentially tasting their environment as they swim through it. These chemical senses are far more useful in caves than vision would be, allowing the fish to locate resources in an environment where those resources are widely scattered and infrequent. Another common feature of troglobites is the loss of pigmentation. In a world without light, there's no need for skin color, no evolutionary pressure to develop protective coloration or camouflage. The result is that many cave creatures are albino or nearly so, pale white or pink, their blood visible through translucent skin. Some cave crayfish are so pale they appear almost ghostly, with long, delicate antennae and legs that look like they might break at the slightest touch. These crayfish are common troglobites in North American caves. There are dozens of species, each adapted to specific cave systems, sometimes to single caves. They grow slowly, live long lives, and reproduce infrequently, all adaptations to the scarcity of food in cave environments. A cave crayfish might live 20 years or more, reaching breeding age only after several years of growth. This slow life history makes them vulnerable to disturbance. If the water quality in their cave changes, or if pollution enters their habitat, they may not be able to reproduce quickly enough to replace themselves, and the entire population can disappear. Cave shrimp are similarly adapted. In Mexican cenotes, the blind cave shrimp Typhlotia is common in the deeper, darker sections of the cave systems. These shrimp are small, typically less than an inch long, with elongated antennae that they wave constantly, sensing their surroundings. They feed on bacteria and organic matter that filters down from the upper layers of the cave system. Like cave crayfish, they grow slowly and live long lives relative to their surface-dwelling relatives. The Mexican blind cavefish, Asternax mexicanus, is perhaps the most studied of all troglobites. This species exists in two forms: a normal, eyed, pigmented form that lives in surface waters, and a blind albino form that lives in caves. The two forms can interbreed and produce fertile offspring, making them ideal for studying the genetic changes that accompany adaptation to cave life. Scientists have identified specific genes responsible for eye loss and pigmentation loss, and they've discovered that these changes happened independently in different cave populations, an example of convergent evolution. What's particularly interesting about Asternax is that the blind, cave-dwelling form seems to have evolved relatively recently, perhaps within the last few million years. Some cave populations may be only tens of thousands of years old. This means that the adaptation to cave life can occur relatively quickly in evolutionary terms, with major changes accumulating over just a few thousand generations. But not all life in underwater caves is blind and pale. In the zones closer to cave entrances, where some light penetrates, there exists a transition zone inhabited by species that are less specialized. Small fish may venture into these twilight zones during the day, hiding from predators, then emerge to feed in open water at night. Certain shrimp and crabs can live in both lit and dark zones, showing some reduced pigmentation but retaining functional eyes. The cenotes of Mexico host a particularly diverse community. In the open water at the center of a cenote, where sunlight reaches, there may be normal fish species, turtles, even the occasional crocodile. As you move into the passages that lead away from the open water, you enter darker zones, and the species change. The normal fish give way to species more adapted to low light, then eventually to the true troglobites that never see daylight. One of the challenges for cave ecosystems is the scarcity of food. In most ecosystems, the base of the food chain is photosynthetic organisms, plants, algae, photosynthetic bacteria. These organisms capture energy from sunlight and make it available to other creatures. But in caves there is no sunlight, so there can be no photosynthesis deep in the system. Cave ecosystems must rely on imported energy. This energy comes in several forms. Organic matter can wash into caves during floods, carrying nutrients from the surface. Bat guano, in dry caves that bats inhabit, provides a rich source of nutrients that supports entire food chains. In underwater caves, organic matter can drift in with the tides, bringing with it a feast of dissolved nutrients and tiny particles. Bacteria consume this organic matter, and then larger organisms eat the bacteria, and so on up the food chain. Some caves harbor chemosynthetic bacteria that derive energy from chemical reactions rather than from light. These bacteria can process compounds like hydrogen sulfide, using the chemical energy released when they convert it to sulfate. Such bacteria are common in the deep zones of blue holes where hydrogen sulfide is present. They form mats and colonies on surfaces, and they support communities of specialized creatures that feed on them. The result is an ecosystem that operates on an energy budget far smaller than surface ecosystems. Cave creatures grow slowly, move little, and reproduce infrequently to conserve energy. Many have slow metabolisms that allow them to survive for long periods without food. Some cave fish can go months between meals if necessary, living off stored body fat and slowing their metabolic processes to a bare minimum. This fragility of cave ecosystems is a concern for conservation because populations are small, reproduction is slow, and species are often endemic to single caves. They are vulnerable to extinction. Pollution that enters the groundwater can wipe out entire populations. Changes in water flow caused by human activities can alter cave conditions enough to make them unsuitable for resident species. Many cave species are listed as endangered or threatened, and protecting them requires protecting entire groundwater systems, not just the caves themselves. Yet despite their fragility, cave ecosystems persist and even thrive in their own terms. They represent millions of years of evolution fine-tuning life to exist in the most unlikely environments. They show us that life is adaptable beyond our easy imaginings, capable of finding ways to survive in places that seem utterly hostile. And they remind us that even in eternal darkness, even in environments devoid of the sunlight that powers most life on Earth, the spark of life continues, quietly, patiently, in forms strange and beautiful. As you settle deeper into rest, imagine these creatures in their dark world, a pale crayfish feeling its way across stone with long, delicate antennae, a blind fish hovering in crystal clear water, sensing the faint currents created by some distant movement, bacteria forming mats on the walls, processing chemicals, turning poison into sustenance. All of them living their slow lives in complete darkness, unbothered by the absence of light, perfectly adapted to their sunless realm, peaceful in their way, continuing the ancient business of life in the quiet spaces beneath the earth. The Yucatan Peninsula, in southeastern Mexico, is a vast platform of limestone hovering above one of the world's most extensive systems of underwater caves. This platform has no surface rivers. All the water that falls as rain sinks through porous limestone into an underworld of subterranean rivers and lakes. The only surface access to this hidden water system comes through cenotes, the natural sinkholes that pierce the limestone ceiling, creating portals between the world of light and the world of darkness below. For the ancient Maya who inhabited this land for thousands of years, cenotes were not mere water sources, they were sacred places, literally entrances to Xibalba, the Mayan underworld. The word cenote itself comes from the Mayan term dozon, meaning sacred well. The Maya built some of their most important cities around prominent cenotes, understanding that these openings provided not just water but a connection to the divine realm beneath the earth. The significance of cenotes in Mayan religion cannot be overstated. They were seen as homes of the rain god Chak, as well as gateways to the afterlife. Ceremonies were conducted at cenotes, including sacrifices intended to appease the gods and ensure adequate rainfall for crops. Archaeologists have recovered extraordinary artifacts from cenotes: jewelry, ceramics, obsidian blades, copper bells, and carved figurines. These were offerings thrown into the waters, gifts to the gods below. In some cenote, particularly the sacred cenote at Chichen Itza, human remains have been found. These appear to be sacrificial victims, individuals thrown into the deep waters as ultimate offerings to the gods. While modern sensibilities are disturbed by this practice, for the Maya it represented the most sacred possible gift, sending messengers directly into the realm of the gods to carry prayers and petitions. Today, cenotes number in the thousands across the Yucatan. Each one is unique. Some are open pools where the entire roof has collapsed, creating something resembling a natural swimming pool surrounded by jungle. Others are more enclosed, with only a small opening at the surface, requiring you to descend steps or a ladder to reach the water. Still others are entirely underground, accessible only by swimming through passages from other cenotes, vast chambers that have never seen direct sunlight. Grand Cenote, near Tulum, is one of the most visited. It's partially open to the sky, with sections of roof remaining to create overhangs and shaded areas. The water is shallow enough for snorkeling at the edges, and the clarity is exceptional. Sunlight streams through the opening, creating beams that illuminate the cavern like natural spotlights. Small fish dart through these beams, and occasionally freshwater turtles surface to breathe before diving back into the depths. As you swim toward the back of the cenote, you enter passages that become progressively darker, eventually leading to sections where divers with lights are necessary to continue. Cenote Kill, near Chichen Itza, presents a different character. This cenote is about 85 feet deep, perfectly circular, with walls covered in hanging vines and vegetation. The opening is about 80 feet across, and from the water's surface, looking up, you see a perfect circle of sky framed by green plants. Waterfalls trickle down the walls, fed by small underground streams. Tour groups visit this cenote regularly, swimming in its deep waters, unaware of the sacred significance it held for the people who lived here centuries ago. The system of caves connecting the cenote is almost beyond comprehension in its extent. Sistema Sakaktan and Sistema dos Ogos together comprise nearly 400 miles of surveyed passage, and exploration continues. New sections are mapped regularly. Some passages are vast galleries where 3 divers can swim side by side with room to spare. Others are restrictions, where a diver must remove their equipment and push it ahead to squeeze through. The passages run at multiple levels, stacked on top of each other, carved at different times when sea levels were at different heights. Mapping these passages requires extraordinary skill and patience. Divers lay permanent guidelines through the caves, thin ropes attached at intervals to the walls with small weights or wedged into cracks. These lines serve as navigational aids, allowing divers to find their way back to exits in the complete darkness of the deeper passages. The lines are marked at intervals with directional markers indicating which way leads toward exits. Without these lines, a diver who becomes disoriented in the cave would almost certainly perish, unable to find the way out in the labyrinth of passages. The water in these passages is the clearest on Earth. It has been filtered through hundreds of feet of limestone over hundreds of years. There are no particles, no plankton, no sediment. Visibility routinely exceeds 300 feet. You can hover in a large gallery and see from one end to the other, every stalactite perfectly visible, every wall clearly defined. The experience is surreal, like flying through a vast cathedral carved from stone and filled with invisible liquid. The halocline in cenote passages is often visible as a wavy, shimmering boundary where fresh rainwater floating on top meets denser saltwater that has intruded from the ocean through cracks deep in the limestone. Crossing this boundary feels like passing through a different medium, as if the water has different density, different resistance. The visual distortion at the halocline can be disorienting, and some divers describe feeling dizzy as they pass through it. Archaeological discoveries in the cenote passages continue to this day. In some passages, human bones have been found dating back more than 10,000 years, from the late Pleistocene when the caves were dry and the sea was lower. These are some of the oldest human remains in the Americas, and they suggest that people were exploring these caves even in that distant time, perhaps using them for shelter, perhaps conducting ceremonies in their dark depths. The ecology of cenotes is unique. In the open lit sections, there are fish, turtles, aquatic plants, all living on energy from sunlight. As you move into the passages away from light, the ecosystem changes. The true troglobites appear: blind fish, pale shrimp, translucent isopods and amphipods. These creatures live their entire lives in darkness, never seeing the sky, never knowing sunlight, perfectly content in their eternal night. The Yucatan Aquifer, accessed through cenotes, is the sole source of fresh water for the entire region. There are no surface rivers or lakes. All human habitation, from ancient Mayan cities to modern resort towns, depends on groundwater drawn from the cenote system. This creates a conflict between development and conservation. Pollution from human activity can enter the groundwater and spread through the entire cave system. Sewage, chemicals, even sediment from construction can degrade water quality over vast areas because everything is connected underground. Conservation efforts focus on protecting the aquifer and the unique ecosystems it contains. Many cenotes are now protected sites. Some are restricted to scientific research only, closed to recreational diving. Others are open to visitors but carefully managed to minimize impact. The goal is to balance human use of these sites with the need to preserve them for future generations and to protect the species that live nowhere else. As you drift towards sleep, imagine descending into a cenote. The sunlight filters down through crystal water, creating rays and beams that illuminate ancient stalactites. You swim slowly through a passage, following a guideline deeper into the earth, entering sections where no light reaches, where you exist in your own small bubble of illumination, surrounded by vast, patient darkness. You feel the cool water on your skin, hear only your own breath, move through a world carved over hundreds of thousands of years, sacred to those who came before, still holding its mysteries, still harboring life in its darkest reaches, peaceful beyond words. Exploring underwater caves requires a combination of skill, equipment, and mindset that goes far beyond conventional scuba diving. Cave diving is considered one of the most technically demanding and potentially dangerous forms of diving, yet it has drawn thousands of explorers who are willing to undergo rigorous training to access these hidden spaces and who contribute to our scientific understanding of these environments. The basic challenge is simple to state but difficult to overcome. Underwater caves are overhead environments. Unlike open water diving, where you can surface at any moment if you encounter a problem, cave diving means you may be hundreds or thousands of feet from the nearest exit. If something goes wrong, if your equipment fails, if you become disoriented, you cannot simply swim upward. You must find your way back through the cave, following the path you came, before you run out of air. This simple fact changes everything about how cave diving is conducted. Cave divers use multiple redundant systems. They carry at least 2 independent air supplies, usually more. If one regulator fails, they immediately switch to the backup. They carry multiple lights, because in the complete darkness of a cave, losing your light can be instantly fatal. A typical cave diver might carry a primary light and 2 or 3 backup lights, all carefully maintained and tested before each dive. The most critical piece of cave diving equipment is the guideline. This is a continuous line that runs from the entrance of the cave along the route the diver takes. In already explored caves, permanent lines are installed, secured to the walls or floor at regular intervals. Divers tie off their own safety line to these permanent lines, creating a continuous connection back to the exit. If visibility drops to 0, which can happen quickly if sediment is disturbed, the diver can follow the line by touch alone, hand over hand back to safety. Visibility management is crucial. Cave floors are often covered with fine silt that has accumulated over centuries. This silt is incredibly light and fine, and the slightest disturbance can send it billowing into the water, reducing visibility from hundreds of feet to 0 in seconds. Cave divers learn precise buoyancy control and swimming techniques that minimize disturbance to the silt. They move slowly, deliberately, never allowing their fins to touch the bottom, never brushing against walls. Even their exhaled bubbles must be controlled, as bubbles hitting the ceiling can dislodge sediment that then sinks down through the water. Navigation in caves requires constant awareness. Divers must continuously track their route, noting distinctive features, watching for line markers, staying oriented relative to the guideline. It's easy to become disoriented in the uniform darkness, where every chamber looks similar. Some passages branch, rejoin, and branch again. Without careful attention to the guideline and to markers indicating direction, a diver can easily make a wrong turn. The rule of thirds is fundamental to cave diving gas management. Divers plan to use 1/3 of their air supply, entering the cave, 1/3 returning, leaving 1/3 in reserve for emergencies. This seems conservative, but it provides a safety margin that has saved countless lives. If you encounter a problem on the way out, if you have to assist another diver, if you take a wrong turn and have to backtrack, that reserve third gives you the air you need to handle the situation. But even with all this training and equipment, cave diving remains unforgiving of mistakes. Small errors can cascade into fatal situations. This is why cave diving has rigorous certification requirements. Before attempting cave diving, divers must complete specialized training, often requiring dozens of training dives over multiple courses. They must demonstrate mastery of equipment, perfect buoyancy control, navigation skills, emergency procedures, and the judgment to abort a dive if conditions become questionable. The scientific value of cave diving exploration is substantial. Cave systems provide records of past climates preserved in stalactites and stalagmites. By drilling cores from these formations and analyzing their growth rings and chemical composition, scientists can reconstruct temperature and rainfall patterns from hundreds of thousands of years ago. This data helps us understand natural climate variability and provides context for current climate change. Cave systems also preserve unique ecosystems. Species found in caves may exist nowhere else on Earth, having evolved in isolation for millions of years. Studying these species can teach us about evolution, adaptation, and the limits of life. Some cave organisms have potential applications in medicine or biotechnology, producing unusual compounds adapted to their extreme environment. Archaeological discoveries in caves continue to reshape our understanding of human history. The bones found in cenotes and blue holes, the artifacts recovered from their depths, the evidence of ancient habitation or ceremony, all contribute pieces to the puzzle of how humans spread across the continents and how they lived in ancient times. Some of the oldest human remains in the Americas have been found in flooded caves, preserved in conditions that would have destroyed them if they'd been on the surface. Geological research benefits from cave exploration as well. Mapping cave systems helps us understand groundwater flow, aquifer structure, and the history of sea level changes. The presence of multiple levels of passages, each representing a different sea level, allows geologists to reconstruct the complex history of ice ages and warming periods. The orientation of stalactites can indicate past earthquakes or tectonic movements. New technologies continue to improve cave exploration. Side-scan sonar can map passages without requiring divers to enter them, though this technology works best in water-filled passages rather than in caves with complex formations that scatter the sonar signal. Remotely operated vehicles can explore sections that are too deep or dangerous for human divers, though their movement can disturb silt and they lack the judgment that an experienced diver brings to exploration decisions. Three-dimensional mapping using photogrammetry allows researchers to create detailed virtual models of cave systems. Divers take thousands of photographs from different angles, and software stitches these photos together into three-dimensional models that can be explored virtually. These models preserve a record of the cave's current state and can be used for research, education, and even for planning future exploration. The longest underwater cave systems rivaled the longest dry caves on Earth. Sistema Ox Belhar in Mexico measures more than 215 miles of surveyed passage. Mammoth Cave in Kentucky, the longest known cave system in the world, is about 420 miles of passage, but much of that is dry. The underwater systems may eventually prove to be longer as they connect across vast areas, and much of them remains unexplored. As you rest, imagine the patient work of exploration, a diver hovering in absolute darkness, unreeling a new line into virgin passage, moving forward slowly, cautiously, into spaces no human has ever seen. Behind them, the line leads back to safety, to light, to the surface world. Ahead lies only darkness and the unknown. They move forward anyway, driven by curiosity, by the desire to see what lies in the unexplored reaches, by the human need to map and understand our world, even its most hidden corners. They are peaceful in their concentration, focused, aware, moving through liquid night with the confidence of skill and training, gradually extending the map, adding new rooms and passages to our collective knowledge, expanding the boundaries of the explored world one chamber at a time. To truly understand underwater caves, we must adjust our sense of time. The formations we've discussed, the systems we've explored, all operate on timescales that make human life seem like a brief flicker. A stalactite takes 1,000 years to grow an inch. A cave system might develop over 1,000,000 years. The oldest caves on Earth have been forming for tens of millions of years. This is deep time, geological time, time measured not in generations or centuries but in epochs. Consider the patient work of a single water drop. It falls from a crack in the ceiling, hangs for a moment, deposits its infinitesimal contribution of calcium carbonate, and falls. The deposit it leaves is thinner than a human hair. Another drop follows, maybe seconds later, maybe minutes. Each drop contributes its microscopic layer. Over the course of a year, the accumulation might be visible only under magnification, a fraction of a millimeter. Over a century, perhaps a millimeter. Over 10,000 years, an inch. Over 100,000 years, a foot-long stalactite. This is not just slow growth. This is growth so gradual that it's functionally invisible to any human observer. You could watch a stalactite every day of your life and never see it change. Yet the change is happening, molecule by molecule, drop by drop, with absolute reliability. The process never hurries. It cannot be rushed. It simply continues, indifferent to any observer, following the inevitable logic of chemistry and gravity. The formations in underwater caves are frozen at the moment the caves flooded. They stopped growing 10,000 or 15,000 years ago when rising seas filled the chambers. Since then, they haven't changed. They are perfectly preserved, held in stasis by the water, waiting in darkness. The stalactite that was growing when the water came is exactly the same today as it was then. Not a single molecule has been added. It's as if time stopped for these formations, while the world above continued its rush forward. This preservation of ancient conditions is one reason underwater caves are so valuable for scientific research. Ice cores from glaciers preserve bubbles of ancient atmosphere, allowing scientists to measure past carbon dioxide levels and temperature. Tree rings preserve records of rainfall and temperature during the tree's lifetime. But stalactites and stalagmites can preserve even longer records, in some cases extending back hundreds of thousands of years. The chemistry of the minerals in a stalactite reflects the conditions when those minerals were deposited. The ratio of oxygen isotopes in the calcite indicates temperature. The thickness of growth rings reflects the amount of water available, which in turn reflects rainfall. The presence of certain trace elements can indicate vegetation patterns, volcanic activity, or other environmental conditions. By carefully analyzing stalactites and stalagmites, researchers can reconstruct detailed climate records spanning timescales far longer than any human records. Some of the oldest individual stalactites are hundreds of thousands of years old, perhaps even over 1,000,000 years. They began forming in caves that were already ancient during ice ages, that humans would not witness for hundreds of millennia. They grew through multiple glacial cycles, adding layers during warm periods when more water was available, adding thinner layers during cold, dry ice ages, when less water percolated through the limestone. Each growth ring is a slice of ancient climate, preserved in stone. The caves themselves are even older. Most limestone caves began forming millions of years ago. The limestone rock they're carved from is often tens or hundreds of millions of years old, formed from shells and skeletons of marine creatures that lived when dinosaurs still walked the earth. The process of cave formation itself takes hundreds of thousands to millions of years, depending on the size and complexity of the system. Consider Sistema Sagittune with its 200+ miles of passage. This didn't form overnight, or even over 10,000 years. This required millions of years of water slowly dissolving limestone, creating passages, enlarging chambers, working through the rock grain by grain. The sections at different levels, carved at different ancient sea levels, each represent distinct periods separated by tens or hundreds of thousands of years. The blue holes we explored are vertical cuts through this history. As you descend a blue hole, you pass through layers that were formed at different times. A ledge at 100 feet might mark a period when sea level was stable at that height for thousands of years, allowing waves to erode a horizontal notch. A different ledge at 200 feet represents an earlier time, perhaps during an ice age, when seas were lower. Each ledge is a bookmark in the planet's climatic history. This layering of time is calming in its own way. It reminds us that our own concerns, our daily worries and stresses, exist in a moment so brief as to be almost immeasurable compared to the lifespan of a cave. The formations we've discussed were forming long before humans existed, and will continue their slow transformation or preservation long after humans are gone. They are patient beyond all measure, content to exist, to slowly change or to remain changeless, indifferent to the rushing pace of the surface world. The creatures that live in caves also operate on different timescales. Cave fish may live 20 or 30 years, extremely long lives for their size. They grow slowly, reaching maturity only after several years. A female might produce just a few dozen eggs in her lifetime, compared to thousands or millions for surface fish. Everything about cave ecology operates in slow motion, conserving energy, never hurrying. Even the water itself moves slowly in many cave systems. Some passages have currents, driven by tides or by pressure differences between connected cenotes. But in many sections, the water is nearly still, moving perhaps a few inches per hour, or not moving at all. Without wind, without waves, without temperature gradients to drive convection, the water simply rests, held in stone chambers, clear and cold and patient. This stillness, this patient continuance, is perhaps the most calming aspect of cave environments. Everything exists in a state of near timelessness. Change happens so slowly as to be imperceptible. The darkness is constant. The temperature barely varies. The stone has been there for millions of years and will remain for millions more. In such a place, the concept of hurry becomes meaningless. There is only the eternal present, the slow rhythm of chemical processes, the occasional passage of a blind fish, the steady drip of water that might or might not be depositing its mineral grain. As you drift deeper into sleep, imagine yourself becoming part of that timeless rhythm. Your breathing slows to match the patient drip of water. Your heartbeat aligns with the deep pulses of the earth. You exist in a moment that stretches backward and forward, connected to all the moments before and after, part of the long, slow story of water and stone, of darkness and life, of the quiet depths where time moves to its own ancient rhythm, unhurried, eternal, peaceful beyond measure. Beneath our feet, largely unseen and often unsuspected, lies a world as extensive and complex as the surface world. The cave systems we've been exploring are not isolated pockets, but parts of vast interconnected networks. Passages link to other passages, cenotes connect to other cenotes through submerged tunnels, and blue holes open into horizontal caves that extend for miles through the limestone. The scale of this underground connectivity is only now beginning to be appreciated as exploration continues and previously separate systems are proven to be connected. In the Yucatan, the interconnected nature of the cenote systems means that what happens in one location can affect areas many miles away. Pollution entering the groundwater at one cenote can spread through the entire network. Conversely, conservation efforts that protect the aquifer benefit all the cenotes and caves that draw from that aquifer. The system is unified, a single vast hydrological structure with thousands of access points. The underground rivers that flow through these passages are true rivers, sometimes carrying substantial volumes of water. They respond to rainfall, swelling during wet seasons and diminishing during droughts. They flow toward the ocean, following the gentle gradient of the limestone platform, eventually emerging at coastal springs or seeping directly into the sea through countless small fissures. The journey of a raindrop from the surface to the ocean might take decades or even centuries as it percolates through soil, filters through limestone, enters a cave passage, flows slowly toward the coast, and finally merges with salt water. The mixture of fresh and salt water in coastal cave systems creates unique conditions. Where the two meet, a halocline forms that wavy boundary we've discussed. But this boundary isn't static. It shifts with the tides, moving up and down inland and seaward as the ocean rises and falls. During high tide, salt water pushes farther inland into the cave systems. During low tide, fresh water pushes back toward the ocean. This daily rhythm creates a mixing zone where neither fresh nor salt water dominates, a brackish layer where specialized organisms adapted to variable salinity can thrive. The tidal influence extends far into cave systems, sometimes for miles from the ocean. Cenotes that are kilometers from the coast can still experience tidal fluctuations, small rises and falls in water level as the ocean pulls and pushes on the aquifer. This demonstrates how thoroughly connected these systems are, how every part communicates with every other part through the liquid medium of the water. Some cave systems connect to deep ocean waters as well as to coastal zones. Deep blue holes may be connected to passages that extend horizontally at various depths, like branches from a tree trunk. These passages might connect the blue hole to other blue holes, or they might dead end in chambers that have no other entrance. Mapping these connections requires extensive exploration, as divers must follow each passage to its end to determine whether it connects to other features. The discovery that separate cave systems are actually connected has changed the rankings of the world's longest caves multiple times. What were thought to be two separate systems turn out to be connected by a single passage, and suddenly the combined system is far longer than either system was individually. Sistema Sakaktoon and Sistema dos Ojos were separate for many years until divers found the connection passage, at which point they became one system measured at more than 400 kilometers of passage. Groundwater flow in these systems is driven by multiple factors. Gravity pulls water downward and toward the ocean. Pressure differences between areas of high and low water levels create flow. Tides push and pull. Temperature differences, though small in caves, can create density differences that drive slow circulation. All these factors combine to create patterns of flow that are complex and sometimes counterintuitive, with water moving in unexpected directions or remaining still in areas where you'd expect flow. The chemistry of cave water reflects its journey and its sources. Water that has recently entered from the surface through a cenote might be fresh, oxygenated, perhaps slightly acidic from dissolved carbon dioxide, relatively warm. Water that has been in the system for decades, slowly filtering through limestone, might be more mineralized, cooler, with less oxygen. Saltwater intrusion brings dissolved salts and different mineral content. All these different water masses meet and mix in the cave passages, creating gradients and boundaries. The biological connectivity of cave systems is equally important. Species can potentially move through the passages, though most cave-adapted species are not strong swimmers and tend to stay in limited areas. But the occasional individual might travel through passages, potentially colonizing new areas. This connectivity means that cave ecosystems are not entirely isolated. Gene flow can occur between populations separated by miles, preventing inbreeding and maintaining genetic diversity. Human impact on surface water can affect entire cave systems. Agricultural runoff, sewage, industrial pollution, all can enter the groundwater and spread through the caves. Because the water moves slowly and the systems are so extensive, pollution can persist for decades, affecting water quality over vast areas. This makes groundwater protection crucial not just for human water supplies, but for the preservation of cave ecosystems. Conservation efforts increasingly focus on protecting entire aquifer systems rather than individual caves or cenotes. The connectivity means that piecemeal protection doesn't work. You can't protect one cenote while allowing pollution to enter the system at other points. The only effective approach is watershed-level management, controlling what enters the groundwater across entire regions. As exploration continues, our understanding of these interconnected systems grows. New passages are mapped regularly, extending the known length of existing systems or connecting systems that were thought to be separate. The total length of underwater caves mapped worldwide increases every year, not just from exploration of new caves, but from the discovery that known caves extend farther than previously suspected. Imagine as you rest, this vast underground world, passages branching and rejoining, chambers stacked on multiple levels, underground rivers flowing in darkness, all connected, all part of a single hydrological system. Water entering the system today might not reach the ocean for a century. A fish in one cento might be a distant relative of fish in a cento 10 miles away, connected through passages that have never seen light. Everything is linked, part of a hidden geography beneath the surface, extensive, complex, and largely unexplored, holding secrets still to be discovered, continuing its patient existence in darkness. Underwater caves have existed for millions of years and will continue to exist for millions more. But their condition, their water quality, and the life they support are increasingly influenced by human activities. As we look to the future of these spaces, we must balance the desires to explore them, to study them, to visit them, and to protect them for future generations. The greatest threat to underwater cave systems is water pollution, because these systems are connected to surface water sources. And because water moves slowly through them, pollutants can persist for decades or centuries. Agricultural chemicals, sewage, industrial waste, even sediment from construction projects can enter the groundwater and affect cave conditions. Some pollutants are toxic to cave life. Others alter water chemistry in ways that affect cave formations or that make the water unsafe for human contact. In the Yucatan, rapid development of the coast for tourism has created new pressures on the cenote systems. Hotels, restaurants, and homes need sewage treatment, and not all development has adequate infrastructure. Some sewage enters the groundwater, bringing nutrients that can alter cave ecology. Nutrients encourage bacterial growth, which can cloud the water, reducing the clarity that makes these caves so special. Bacteria can also consume oxygen, creating anoxic zones where cave life cannot survive. The solution requires comprehensive groundwater management. This means treating sewage properly before it can enter the aquifer. It means controlling agricultural runoff and limiting the use of chemicals that can leach into groundwater. It means careful management of development to ensure that increased water use and waste production don't overwhelm natural systems. These are challenging tasks requiring cooperation between governments, businesses, and local communities. Conservation efforts also focus on limiting physical impact to caves. Uncontrolled diving can damage formations. A careless fin kick can snap a stalactite that took thousands of years to grow. Touching formations can leave oils from skin that alter the surface, preventing future mineral deposition. Guidelines for responsible cave diving include staying well away from formations, maintaining perfect buoyancy to avoid accidental contact, and never touching anything unless absolutely necessary for safety. Some caves are now closed to recreational diving to protect them. These caves might be open only to scientific researchers, or they might be closed entirely, left undisturbed to preserve them in their natural state. Other caves are open but require specialized certification before entry, ensuring that only trained divers with proven skills can visit. Some of the most popular cenotes have installed platforms and marked routes to direct swimmers away from sensitive areas. The balance between access and protection is difficult. People who have never experienced underwater caves cannot fully appreciate why they need protection. Allowing limited access helps build support for conservation, but too much access can degrade the very qualities people come to experience. Finding the right balance requires ongoing management and monitoring. Scientific research in caves continues to yield valuable discoveries. Studies of cave formations provide data on past climates that help us understand natural climate variability and place current changes in context. Research on cave ecosystems teaches us about evolution, adaptation, and the diversity of life. Archaeological discoveries in caves provide insights into human history and migration patterns. All this research requires access to caves, but responsible research access that minimizes impact. New technologies may help both exploration and conservation. Remote sensing techniques might allow mapping of passages without requiring human entry. Improved water monitoring could detect pollution sources quickly, allowing faster response. Better treatment technologies could remove pollutants from groundwater, protecting aquifer quality. Advances in genetics might help us understand cave species and their conservation needs better. The exploration of underwater caves is far from complete. Most cave systems are only partially explored. Many blue holes have been mapped only at their entrances, their deeper reaches and connecting passages remaining unknown. New cenotes are still being discovered in the Yucatan as development spreads into previously remote areas. The total extent of the world's underwater caves is unknown, but it certainly measures in the thousands of miles, possibly tens of thousands. Each year brings new discoveries. A passage that was thought to end turns out to continue, requiring only that divers pass through a narrow restriction. A seemingly isolated cenote is found to connect to a major cave system. A new species is described from a remote section of a blue hole. The longest underwater cave gets longer as exploration continues. Our map of the underground world continues to expand, slowly, passage by passage, chamber by chamber. Future generations will inherit these caves, whether pristine or degraded, protected or exploited, understood or ignored. The choices we make now determine what they will find. If we protect groundwater quality, if we limit impact from visitation, if we support research and exploration while respecting the fragile nature of these systems, then future generations will experience the same wonder we experience today. They'll dive through crystal clear water past ancient formations, encounter unique species, explore passages that connect to the deep history of the Earth. But if we allow pollution to degrade water quality, if we permit uncontrolled visitation to damage formations, if we ignore the needs of cave ecosystems, then future generations will inherit something diminished. The water might be cloudy, the formations might be damaged, the unique species might be extinct, having survived for millions of years only to disappear on our watch. The choice is ours. The good news is that awareness is growing. More people understand that underwater caves are not just curiosities, but are valuable natural resources deserving protection. Scientists study them, conservation organizations work to protect them, governments designate them as protected areas, and divers who visit them increasingly understand the need to minimize their impact. The trajectory is generally positive, though much work remains. As you rest tonight, imagine these caves continuing into the distant future. Thousands of years from now, assuming we make the right choices, these spaces will still exist. The water will still be clear, filtered through ancient stone. The formations will continue their patient growth if conditions allow, or will wait in preserved perfection if submerged. The blind fish will still navigate their dark passages, evolved and adapted to their eternal night. And perhaps far in the future, explorers will swim through these same passages, experiencing the same wonder we experience today, grateful that we chose to protect these places rather than allow them to be damaged or destroyed. Now, as our journey through underwater caves comes to a gentle end, let yourself rest completely. Your breathing has slowed, matching the patient rhythm of water dripping in darkness. Your body has relaxed, floating in your mind's eye through crystal clear water. Your thoughts have quieted, like sediment settling after a diver has passed, leaving only clarity. You've traveled tonight through some of the most ancient and peaceful places on Earth. You've seen formations that grew for thousands of years in perfect darkness. You've met creatures that have evolved to thrive without ever knowing sunlight. You've descended into blue holes that plunge into the mysterious depths, and you've drifted through cenotes that the ancient Maya considered sacred portals to another world. These places exist right now, even as you rest. Somewhere in the Yucatan, moonlight is touching the surface of a cenote, creating ripples that send patterns of light dancing across stalactites in the shallow cavern below. In the Bahamas, the tide is flowing in a blue hole, pulling water through passages that have known such flow for thousands of years. In caves beneath the Turks and Caicos, blind shrimp are sensing their way along the walls, living their slow lives in the eternal night. All of this continues, patient, timeless, untroubled. You are connected to these places by more than imagination. The water you drank today may have once flowed through underground passages. The limestone that forms these caves came from sea creatures that lived hundreds of millions of years ago. The calcium in your bones is the same element that slowly builds stalactites, drop by drop. We are all part of the same planetary system, the same cycles of water and minerals, the same long story of life adapting to every available niche. Let that connection bring you peace. You are not separate from the natural world, not isolated or alone. You are part of something vast and ancient, part of cycles that began long before humans existed and will continue long after we're gone. There is comfort in that continuity, in knowing that you are part of something so much larger than your individual concerns and worries. As you drift towards sleep, imagine yourself floating in a cenote. The water is perfectly clear, perfectly still. Above you, a circle of stars is visible through the opening to the surface. Below you, the passage descends into soft darkness, not frightening but welcoming, a gentle gradient from light to shadow. You are weightless, suspended, held by the water, safe and secure. You let yourself sink slowly, gently, deeper into the darkness. The stars above grow more distant, the light fades, but you're not afraid. The darkness here is peaceful, comforting, like the darkness behind your closed eyelids as you rest. You continue to sink, slowly, softly, down into the quiet depths where nothing demands your attention, where there is only stillness and peace. The walls of the cenote pass by on either side, barely visible, marked with ancient patterns carved by water. You drift past stalactites, hanging in the darkness, monuments to deep time. You float through a halo climb, that shimmering boundary, and the water feels slightly different, slightly denser, cradling you more securely. You continue your gentle descent, unhurried, at peace, letting the water carry you deeper into rest. You come to rest on soft sediment at the bottom of the passage. The sediment is fine, like silt, and you settle into it gently. Around you is darkness, complete and profound. Above you, somewhere far away now, is the surface world, with its noise and rush and constant demands. But here, there is only silence, only stillness, only the patient, eternal calm of the deep places. You are safe here. You are held by the earth itself, cradled in ancient stone, surrounded by water that has been purified by its long journey. Nothing can disturb you here. No sound reaches you. No light penetrates. There is only the deep, profound peace of resting in the womb of the earth, in spaces carved by time beyond imagining, in darkness that has existed since long before humans, in silence so complete it becomes a kind of presence. Your breathing slows further. Your heartbeat quiets. Your thoughts disperse like bubbles rising from a diver, floating up and away, leaving only emptiness, only rest. You are sinking now into sleep, into dreams, into the deep places of your own mind, as calm and ancient and mysterious as the underwater caves we've explored together. The caves will still be there tomorrow. The stalactites will continue their patient growth or their patient waiting. The blind fish will navigate their dark passages. The water will flow, slowly, constantly, from the surface to the ocean and back again in the endless cycle. All of it will continue, unchanged by your absence, patient beyond measure. And you will rest, deeply, completely, held by the same forces that shape caves and build mountains, that move water through stone, that give life to darkness, that connect all things in the great web of existence. You are part of it all, and it is part of you. And in this moment, there is only peace, only stillness, only the gentle, inevitable slide into deep, restful sleep. Rest well. The caves will watch over you in their way, patient and eternal, as you descend into dreams. And when you wake, you'll carry some of their peace with you, some of their patient acceptance of time and change, some of their ancient wisdom that comes from simply existing, unchanged and unchanging, in the deep, quiet places where water and stone dance their slow dance in darkness. Good night.